Okay, so we've talked about a few different graph algorithms, mostly breadth first search and depth first search, but we sort of expanded on both of those. Breadth first search, we also did sort of a shortest path kind of algorithm, and for depth first search, we used it for topological sorts. But what we haven't talked about is actually how do you represent a graph in code. So we'll spend this lecture, these lecture slides talking about that.
Yeah.
So in specific, we'll talk about edge lists, adjacency matrices, and adjacency lists. And then we'll come back to that friend circle problem that we hit on the very first day of class. We'll also talk about weighted edges and graphs with directed edges. For each of these types of graphs, we're going to look at the following questions. How can we count the number of vertices and how long does it take? How do we count the number of edges? How do we add a vertex? How do we add an edge? How do you check if an edge exists? How do you find all neighbors of a vertex? And how much memory is needed to store the graph. So we'll start with undirected graphs with no weights, which look like this. We'll talk a little bit about directed graphs, which just adds arrows there. And just as a reminder, really the biggest difference is here we have an edge going from 0 to 1, and it's also the same thing to say that we have an edge going from 1 to 0. Whereas over here, we only have that 0 to 1 edge. There's no edge going backwards. We'll talk about weighted graphs. So that's a graph where each edge has some sort of value associated with it. So if you're thinking about a graph representing geography, maybe that edge is distance, or maybe it's time to travel between 2 points. We can also have directed and weighted graphs. All right, well, let's talk about our first representation. We'll call this the edge list representation. So for the graph on the right, how do we represent it using an edge list? Well, it's really just exactly what it says. It's a list of edges. So for example, we should have the 0, 1 edge in the graph. We should have the 0, 8 and the 0, 6 edge. Those should all show up there, and I'll put all those in the first row. It doesn't have to be in sort of this sorted order, sorted by the first vertex or the lower vertex. Lower vertex in that 0 comes before 8, 6, and 1. But that's just sort of a reasonable way to put them. So I also have all of the edges coming off of 1. And if you notice, I also have the edge going from 1 to 0. So I don't put that in there twice. You can, but there's not a great reason to put it in there twice. I have all the ones coming off of 2, 3, 4, 5, 6, and 7. So if you notice, I don't have anything coming off of 5 and 6, and that's because it's only connected to vertices that came before it. So the 0 to 6 edge is taken care of here, the 1 to 6 and the 2 to 6. Those show up elsewhere. So that's an edge list representation. So let's start by saying, how do we count the number of vertices and how long does it take? Well, the only way that we can count vertices is to loop over every edge in the list and just check, okay, have I seen vertex 0 before? Have I seen vertex 1? Have I seen vertex 0? Have I seen vertex 6? So we're going to say for each edge in the edge list, and I've abbreviated everything here, so it's EL instead of edge list. I've had to do that abbreviation just to make sure everything fits on the slides. So for each edge in the edge list, we check to see if it's weighted, and I'm doing that just to see if each edge is represented by 0, 1, so that would be like vertex 1 and vertex 2. And then if I have a weighted edge, which we'll talk about later on, I could also have the weight here, so like 0.7. So I'd have vertex 1, vertex 2, and then the weight, the cost between going from one vertex to another. So that's what this little bit here is about, and we can ignore that for now. So what are we going to do? We're going to create a set. And a set is something that doesn't allow for duplicates, essentially. So we're just going to add v1 and v2, because if I add, for example, the vertex 0 multiple times, it's only going to show up one time in the set. So I just loop over every edge and add both vertices to the set. And then finally, I can just return the total number of vertices in that set. And that's going to take big O of m time, because I'm looping over all m edges. All right, next, how do we count the number of edges, and how long does it take? Well, we directly have access to our edge list, and it turns out to count the number of edges, we just have to return the length of that list. In pretty much any list, you have access to that in constant time. How do we add a vertex, and how long does it take? Well, adding a vertex is kind of unusual because we have a list of edges. So if we want to add another one here, let's say we wanted to add a vertex 10. Well, if it's not connected right away to anything else, the only way to do that is to sort of kind of give it an edge to itself. So how do we add a single edge? We just add, how do we add a single vertex? We add a vertex by just sort of saying that we have this vertex and it only is connected to itself. And adding to the end of a list is going to be constant time, or actually, it's probably more accurate to call it amortized constant time. So amortized analysis is something we'll talk about later in the semester. But you have to remember, anytime you're adding to a list, every once in a while it has to double the size of the list and copy everything over, or increase the size of the list. You don't always have to double it. All right, next, how do we add an edge, and how long does it take? Well, again, this one's going to take constant time. We just append the given edge. So instead of making up our own edge this time, we just append the given edge, and that is a constant time operation. Or again, amortized constant. All right, finally, how do you check for the existence of an edge, and how long does that take? Well, as you might expect, to do that, we have to search through the entire list of edges. And the answer to this will depend on if the edges are in some sort of order or not. So for example, like I have in our list of edges here, I don't have to search through it linearly. I don't have to look at every edge. Since I've got them sorted based on, each individual edge itself is sorted based on the lower number. So I have 0 to 1, 0 to 6. I don't have 6 to 0. So that means there's some structure to my edges. And they're also sorted in that I've got 0, 0, 0, then 1, 1, 1, and then 2, 2. So it's easier to find them. But you don't have that guarantee. So we're either going to have to search through all M edges, or we'll have a binary search. And the code for that's going to look like this. So for binary search, I just have a pretty standard iterative binary search. Otherwise, a linear scan through the edges. All right, next, how do I find all neighbors of a given vertex? And if you're not familiar with what a neighbor is, all the neighbors of vertex 7 would be any vertices that it's connected to. So that would be 6 and 0. I would want to get the vertices, 8 and 0, not 6 and 0. Well, you have to loop over all edges. So I'm going to say for each edge in my list of edges, and for this one you can clearly see I'm ignoring the weights. I wish I was a little more consistent in my slides here. I apologize for that. So I'm going to loop over all edges, which is why we have a big O of M algorithm. And for each one, I'm going to say if V1 is equal to the vertex for which I want to find neighbors, then I'm going to append that to my list of neighbors. Otherwise, if V2 is equal to that, I'm going to append V1. So for example, if I want to find everything connected to, let's say, 3. Oh, let's pick a different one. Let's see. Let's say 4. I would say find this one, this one, this one, this one, and this one. So if you notice, sometimes 4 shows up as the second vertex, and sometimes it shows up as the first vertex, which is why I need to check both. And finally, for edge lists, how much memory do they use? Alright, so this time, instead of saying it's T of n plus m, or T of nm, I'm going to say it's m of nm, and that will still be big O of m. I'm going to take the amount of memory that it takes to store each individual edge. So let's say m is my count of edges, and let's say I have 2 vertices per edge, and let's say that each one of those is represented by an integer, so that would be 4 bytes per integer. My memory usage will be m times the amount of space it takes to store each vertex. Each edge, so that's 2 vertices. And then I can also add on, if I have edge weights, I can also add on a floating point number, and we'll just say 8 bytes for that.